All right, thank you, Tom. So, as mentioned, I'm Kevin Pitstick. I'm from the Software Solutions Division at the SCI. And this project Vessel focuses on how we can create container image builds that are reproducible. We are in the first year out of 2 years, so we have another year to go. And so I'll get started with the problem. So right now, many container builds and software builds throughout both industry, the DoD, they're just not reproducible. So you do the build multiple times, and even if you think you have the same inputs, they come out with different outputs for a number of reasons that we'll discuss. And so this really can impact and inhibit trust in the supply chain. So there's a couple documents or frameworks that I have listed there. One is a developer guide released by a few of the DoD organizations, and one of the recommendations they give is for securing your supply chain to have reproducible builds. Also, there's the SALSA security framework. In order to reach the level 4 certification for that, they say that you need to either implement reproducible builds or at least explain why you can't. So the solution, what this project looks into, is how can we, analyze these environments, identify what issues exist in the software and build files for containers, and try to categorize them, and then prototype tools to automatically detect and repair these. And so this all gets back to trying to detect when DoD organizations are building things and detect malicious tampering in the build process. So I'm going to bring up a throwback from a few years ago, the SolarWinds hack that I'm sure you all remember. This was a malware that specifically targeted build servers. It would wait for a build command to happen. It would inject itself into the source code prior to compilation. Once compilation was over, the malware would remove itself. So if you looked at the source code beforehand, you would not see the malware. If you looked afterward, you wouldn't see it. If they had a reproducible build for the software, this is something that they may have been able to detect. As you can see, there was a lot of damages, estimates of millions of dollars of reports. There's a fun quote I won't read by David Wheeler, talking about how this is exactly the kind of malware that reproducible builds is designed to detect. So a little bit of background just to get on the same page terminology-wise. Reproducible build, given the same build environment, you can create bit-by-bit identical copies of all artifacts. As we'll talk a little bit, bit-for-bit reproducibility may not always be reasonable. It may not always be desirable. But it's at least sort of the baseline starting point that we talk about. When I talk about a reproducibility failure, it's an instance when you have two separate builds of the same container image with the same build environment, and you get two different outputs. In this case, that would be the container image. And then these failures occur when you have a reproducibility issue, which is the actual part of the code that makes it not reproducible, and then there's a specific change in an external factor. So there's some examples here. Time is a very common one that we see. New package releases if you depend on upstream sources, but there's a whole number of little things that could make your build not reproducible. Obviously, when we started the project, we're looking at state-of-the-art, what is out there. There are some tools. Actually, we found a lot of the container linting tools, such as Hadalint. They have support for identifying, it turns out some of the best practices, call out things that make your builds reproducible, as expected, but they don't cover all the cases. There's also a reproducible builds project. If you're interested in this sort of thing, I highly recommend looking them up. It kind of comes from the Debian community as they're trying to make their packages and their distribution as reproducible as possible. So there's a lot of tooling out there to do this, and one of the tools that they developed we're actually using within our pipeline itself. But they're sort of focused more on general reproducibility. They're not looking quite into containers themselves. And so our hope is to sort of bring some of these things together and develop this tooling and this understanding of how to address reproducibility in containers. All right, so this is kind of an overview. This is a good distillation of the project in a nutshell, kind of work from left to right. Let's say you have your code repository, that's sort of a known trusted entity. You've got your Docker file, your build scripts, and you've got your pre-build jobs. Where we are sort of interested in inserting ourselves into the CI pipeline with this project is before building images and after building images. And we're really looking at two different kinds of analysis. On the pre-build analysis, we have the linting and repair. So it's pretty self-explanatory. We're looking at the Docker file, potentially some of the build files, and looking for things that might indicate that there's irreproducibility in your build. And then on the flip side, there's the diff tool, which I'm going to be talking about in more depth, that we focused on in year one. And this is really looking at if you have a build environment where you're building the same image 2 times on 2 different runners, you can compare them and try to identify all the differences between them. And then, as sort of shown, all of these tools can kind of output recommendations back to developers, reports that could be used for things like certificate to field, however we'd want to do it. So I'm looking at reproducibility issues. I gave a few examples. Here's a list of kind of high classes of reproducibility issues. Date and time is something that I mentioned. If your build, pulls in date and time into one of the artifacts, log files are things that obviously have a lot of date and time in them. Dependency version pinning, recommended dependencies, package manager caches. There's a whole number of them. The interesting thing to note is that none of the things on this list are malware. These are things that are expected. You would sort of not generally worry about them. But the problem is that it's important to be able to detect and categorize these things so that when a malware does, when something you don't expect to happens to your build, that it kind of lights up like a big red flag. Right now, with all of these other changes happening, it really becomes an insurmountable thing to determine if it's reproducible. So the diff tool is the one I'm going to talk about first, and you will kind of work it left to right. This whole image sort of depicts the different phases. So phase 1 is pulling your images. We're using the Scopio tool that does this in a very reproducible manner. It can pull from Docker registries. Basically, if you have an image that conforms to the OCI standard, it can pull it. Once you have your images, we're using a tool called Yamochi that unpacks them into the file system. And one of the interesting things to note here is that we do kind of, we need root permissions in order to unpack them with the permissions that they come with, because one of the things we do analyze is what permissions are in the container, because that can be very important. Once you have the images unpacked, Diffoscope is a tool that we run against the 2 different folders. Diffoscope comes from the Reproducible Builds community. The great thing about this tool is that it has human-readable comparisons of many binary formats. So a lot of times you may have 2 zip files and 2 different images. If you look at the binary diff, they're very different. But if you actually can analyze it and see what the difference is, you see, oh, it's just a timestamp. And so then there's nothing to worry about. And then the final phase of the tool is we look at the diffs and we categorize them based off of, what kind of file matches there are, what command generated the diff, in the case of like zip files. And we can set a lot of flags to look for very common things that we see across images. And kind of going back to the goal there, this is to help us separate benign versus malicious. The other interesting thing about the diff tool is ideally you come into it with a fairly reproducible image already. If you come in with something that is very unreproducible to start with, you're going to have a lot of things light up. And so that kind of gets to the pre-build tool that we're looking to build more out in the second year can really help you get to a point where you have more confidence that your builds are reproducible. And then the diff tool is useful for kind of both identification, but also for that final verification that everything looks good. As I mentioned with the diff tool configuration, there's a number of things that we set in our configuration file. One of them is you can specify a particular file path. So for example, if we're looking at reproducibility in Git metadata, it's always going to be in that .git folder that's in your repository. We also pull out the file type from libmagic, so you can say I only want to match on files of a particular type. And then there's the ability to basically say, to narrow down and say, okay, what difference in these two files do I want to match on? And so for a timestamp in a log file, you could say, well, there's you can have a regex for the date and the time so that it can flag it as, in these particular log files, we're matching the date and time. And so the tool really just, this configuration file, we come with a set of configurations. We're also going to make that extendable so that if you have particular files within your build environment, you'll be able to create your own rules to match on. And so what comes out of the diff tool? We have a summary, and it's going to tell you these are all the flagged issues that we know about, and then these are the unknown issues. And then it drills down into every single issue, links it back to the unified diff that was generated. And then you can sort of see, okay, for all the flagged issues, you may not care about a large majority of the flagged issues. There may be some you do care about. And so, we'll come with sort of pre-canned recommendations. Like, I don't think anyone really cares too much about the date and the time. However, if your binary files start having differences, then that's something you need to look into more closely. All right, so as we started to get about testing the tool, one of the things we did is we looked at GitHub as our initial source for repositories with Docker files. Going off of some recent papers that have done Docker file analysis, we came up with a set of rules to sort of search GitHub. We're looking for Docker files in the base directory of the repository. We're also looking for repositories that have at least 50 stars. That helps, sift out a lot of the garbage repositories or the student repositories that are out there. And then we went through, we cloned all these repos, we attempted to build, and then we track which ones succeeded, which ones failed, to give us a record in case we want to increase the data set. So we built up this sample data set via sort of an automated fashion in that way. We had about a little over 700 repositories that matched our search criteria. We pulled together the sample data set of about 110. And then we pulled some statistics just to give us a warm feeling that we were, being representative. A lot of shell, Dockerfile, Python code was detected. And then also looked at the last modified year for the repositories. No surprise that most of the things that build successfully are things that have been modified semi-recently. And then for the experiment, as kind of mentioned with our diff tool, we went through kind of one by one, and we built the image one time, and then we built it a separate time. So we used BuildKit to build all of our images and output them in an OCI archive tar file format. And then we ran the Vessel diff tool on both of the images. We found some interesting things. So after some trial and error of hitting the major differences we were seeing, we were able to get about 91% of the differences in each of the repositories, get them flagged. Our goal is kind of up there more at 95%, but it's still a work in progress. A lot of the differences, things like debugging metadata was a very common one, especially for Golang. Golang build cache files, as mentioned, time, inode differences, things like that were all very common things. And we did see a few repositories that had, so many of the repositories were up at 98, 99% of the things we were able to flag. There were a few where we looked at it and we said, only 1% of the differences in the file we were able to detect and flag. And we looked more closely into it, we found that they were actually installing different versions of packages. And so that led to many of the files within them were different. And so that's one of the things that we're focusing on more with kind of the pre-build linting phase of the tool, to basically say, we can look and see if you're pinning your dependencies up front. If you're not pinning your dependencies, it's very likely you might get different software put in your container if you build it at one time versus another time after it's been updated. So we're really looking forward into the next year of having this kind of dual pre-build and post-build to help give a full reproducibility analysis. So looking forward, coming back to this image at the beginning, we have the vessel diff tool is available today at the CMU-SCI GitHub page. We do have the linting and repair tools that we're working on now. We're expecting those to come out later next year, hopefully at that same URL location. And so, as many of the other projects had mentioned, we have another year with this project. We're interested in, DoD groups that, really care about, build reproducibility, and, are building container images, and they have things they'd like to test on. So definitely interested in testing the tool out, and it is free to use, so that is a good part. And also feel free to pull it and try it if you're tech savvy and you want to test it out. We'd love to have any feedback. This was the team, so myself and then Alex, Lehan, and Sebastian. Big kudos to them with doing a lot of the development work. And here's our contact page, and feel free to ask questions.